So that's why in this bar case, we never consider IXX. We usually calculate what? We calculate IYY, IYY or IZZ. We never calculate IXX. But now, if you consider really a bar, a cylinder like this, and the answer IXX is 1/2 of the mass times radius squared. So this R here is the radius. Of your cylinder. So the same formulation for both the cylinder and also for the bar, except for the bar case, you still can calculate the mass moment of inertia along the longitudinal axis, except that this value eventually turns out will be very, very small. So that's why compared to the IYY, IZZ, we just ignore IXX. But if you're provided with information of IXX, you can still calculate it. So let's come back here. You are not provided with the information of the radius of the bar, therefore you can just ignore IXX. That's how we're going to finish our calculation. Now look at the tensor matrix. For the tensor matrix I, we are supposed to have IXX, IYY, and IZZ. IXY, IXZ, IYZ, and this part is symmetric. Just write half of it. Because we said the dimension you're not of the radius of the bar is not provided, you can assume that the IXX is 0. Now, does this object have any axis of symmetry? Does it? Does it have axis of symmetry? Now, for IYY, actually, we already have that before. We said this is 1/12. IYY is 1/12. This is what we did for the example. Remember, it's 1/12 of the total mass times the total length squared. So this is 1 times the square. That's IYY. What about IZZ? The same thing. IZZ is IYY. Think about that. What's IYY? IYY means the bar. I want to spin the bar in this direction with respect to the y axis. Remember, use your thumb to define the direction of rotation, and use your 4 fingers to define the orientation of this rotation. So this is IYY, and IZZ is like this. So IYY means the bar will be spinning, rotating on the XZ plane, and IZZ means the bar will be spinning on the XY plane. So they are the same. Correct? Therefore, IZZ is nothing but just 1/12 ml squared. These two are the same. And this one is so small, so we said approximates to be 0. Now, you notice that this whole thing actually spins with respect to the z-axis, which means the angular velocity is actually a vector. And this angular velocity is 10 times k. Radians per second. That means there's only one angular velocity component of this angular velocity vector. If that's the case, which means you don't have to worry about the IXY, IYXZ, IYZ, because they don't concern you. The rotation is not on either XY plane or the YZ plane or the XZ plane. It's not. Rotation is practically just one component. So you can just ignore this for now. So you don't have to worry about this. You just need to know the 3 of them, which is this one, and this one. Now, let's recall the definition that we used. But before we continue, let's find the values of this, and then we can come back to erase this part and use it. So what is the value of IYY and IZZ? It's 1/12 times the mass. Mass is 5 kilograms. Once again, this is very, very important. I spend a lot of time emphasizing on the difference between mass and weight. So please do not confuse kilogram mass with force, because in metric system, force is carries a unit of newtons. When you see kilogram, it's mass. When you see Newton, it's force. And don't confuse these two. They don't communicate. They don't talk, just like they speak different languages. Don't put these two together. 1/12 times 5 kilograms times length. And the total length is 1 meter over there. So 1 square. And this will give you the value of 1.66. And the unit is kilogram meter square. So we found the IYY, IZZ right here. And next, let's plug them in the Gaussian equation, which you saw it the first time on your notes, but is provided on my notes. I think is page 62 or 68. 68. That's the where I gave you. That part is from my note 68. So step 2, we're going to recall this general form for moment equilibrium in 3-dimensional equation of motion. It's from my note 68. From here, what do we have? We have summation of the moment in x direction equals to the mass moment of inertia xx times the angular acceleration in the x direction. So it's alpha x, right? Minus iy minus iz times the angular velocity in the y direction and the angular velocity in the z direction, or the angular velocity components in the y direction and the z direction. Then what do? That you keep changing the subscript, that you can propagate this form into the other two. So let's take the time, because this may be the last time we're writing this. So let's copy it. You can familiar yourself with this system. The moment equilibrium equals to the mass moment of inertia on the y direction times the angular velocity in the y direction minus the ix. This is actually y, this will be z, minus iz minus ix times the x component of the angular velocity times the y component, z component of the angular velocity. Or moment equilibrium in a z direction equals to the mass moment of inertia in the z direction, izz, times the angular acceleration component in the z direction minus the mass moment of inertia. This actually should be yy, zz, zz, xx, minus the x component of the mass moment of inertia minus the y component of the mass moment of inertia times omega x times omega y. Now, certainly you must have noticed the pattern here. If it is x, this must be x, this must be x, right? And the other two is what? The other two is just this. If you have y here, you must have a y here. You have a z here, you must have a z here. This is the pattern. Okay. Now, let's plug this all in. Then we can look at this one at a time. If we look at x component to see the moment equilibrium. Take the first one. So what do we have for here? Look at the moment equilibrium. If you look at the spinning of the whole thing, right? Does the moment equilibrium that we have means what? Means that the bar that we considered earlier, which is this. The bar is subjected to what forces? First of all, it's subjected to an angular motion, which is angular velocity, right? Omega. What about gravity? Of course, there's a gravity. So when there's considered the center of gravity, there's a weight, which is the mass. Because when you consider mass, what is the weight? That's mass times gravitational acceleration, AG. And in this case, what's the value of AG?